In this module, we will discuss systems that don't have the form of a standard first order or standard second order system. In the past two modules, we've been discussing what we term time response analysis. And in the first two modules in particular, we examined what we call first order systems and second order systems. In Module 12, we will address systems that don't have these standard forms, in particular higher order systems, that is, systems that have more than two poles, systems with zeros, that is, that have S terms in their numerator, and even nonlinear systems. Higher order systems by definition have more than two poles, 3, 4, 5 poles. In general, we can consider the response of a higher order system as the sum of first and second order responses. For example, if we wanted to find the time response of a higher order system, what we can do is we can take the given transfer function and perform a partial fraction expansion. So in this case, we have a third order system. We have one real pole, and then we have a quadratic with two complex conjugate poles. And that's always going to be the case. No matter how high an order system we have, the poles can either be real or complex conjugate. So when we do the partial fraction expansion, we will end up with first order terms that have a real pole, and we will end up with underdamped second order terms that have complex conjugate poles. Therefore, we can consider the response of a higher order system as the sum of first order responses and second order underdamped responses. So this gives some clarification to why or how it is that our understanding of standard first order and standard second order systems provide intuition and understanding of higher order systems. Furthermore, it's often the case that higher order systems can be approximated by first or second order models. For example, in this case, we have two terms, a first order term and a second order underdamped term. It will often be the case that one of these two terms will dominate the response. So even though there's elements of both, it turns out that often will be the case that the response will look like either a standard first order response or a standard second order underdamped response. We will now go ahead and look at this notion of how certain dynamics of a system can dominate. In particular, we're going to look at an example for, in this case, of a second order system, and we're going to try and perform what we call model reduction. That is, we're going to try and take a higher order system and approximate it by a lower order system. With this second order system, we will try and approximate it by a first order system. So one way to think of this system is as two first order systems in series with one another. So the block diagram would look something like this. The one term has a pole at -10, and so its speed of response, or the rate at which it decays, will be proportional to e to the -10t. This other term, however, has a pole at -2, and so its speed will be proportional to e to the -2t. Therefore, if we were to give this system a step input, we were to give g of s a step input, then you can imagine an intermediate signal, which is the response of the first order model, and then the total output of the system then being the output of the second first order system. Looking at this term is much faster than this term. E to the -10t is something that decays quite a bit more quickly than e to the -2t, and you can see that in terms of their response curves. In general, it turns out that the slower dynamics of a model will dominate the dynamic response. So for example, if we took this term, the slower term, and we fed it a straight step, the output would look almost exactly the same. This response is so fast compared to this response that it almost appears as if it were a regular step. And so what we can do is we can, in essence, replace this first system by a static gain that provides the same steady state value as the original dynamic transfer function. And so if we feed this static gain, we're just going to get a scaled version of the step. And then if we feed that step into our system, we're going to get a very similar response to what we have here. It may be such that you can hardly tell the difference. So this is the basic idea that we're going to use in order to do model reduction. If we have a situation where we have complex conjugate poles and there's oscillation, then we need to be a little bit more careful. There's a little bit more nuance to it than just this, but this, I think, is a good example in general. One rule of thumb is that the dynamics of a pole may be neglected if its real part is 5 times greater than the real part of the other poles. This is a pretty good rule of thumb, but it really depends on your situation. It depends on how accurate you need your model to be. It depends on whether or not there's any oscillation or not, and whether or not you want to capture that oscillation or the ringing in the response or not. But even if you neglect the dynamics, even if you take away that transfer function or that pole at s plus 10, you still need to capture its steady state contribution. And that's what we were doing by replacing that first transfer function by a static gain. So we can neglect the dynamics, but we still want to get the same steady state response of the reduced model as we had with the true model. So in this case, this was the example from the previous slide. We have two poles. We have a pole at -2 and a pole at -10, and the slow pole, so the pole at -2 is slower. It has a smaller sigma value. It's closer to the imaginary axis. Since it's slower, it dominates the other pole. And so the idea is that we want to try and get rid of that fast pole and approximate G of S as a first order system with a single pole at S equals -2. But we need to be careful that the reduced model has the same steady state response as the original model. Okay, so that's what we're saying here. We want to take our original model and we want to approximate it by a first order model, but we need to find a gain that makes the DC gain of these two, that makes the steady state response of these two transfer functions equal. And the way that we can determine what K needs to be is by looking at the steady state value of the output, which we can find by using the final value theorem. So in this case, if we consider that G of S is equal to Y of S over U of S, then Y of S is equal to G times U, where U is a unit step. Since we're trying to match the steady state value, we're going to give it a constant input that's not changing, so that we can see what happens when the transient dies out. If we look at this, so here's S times Y of S, where Y of S is G times U. The S from the unit step cancels with the S from the final value theorem, and we're left with the limit as S goes to 0 of G of S, which is equal to G of 0, presuming that the transfer function G is defined at S equals 0. So this is called the DC gain. This is how much scaling is produced by the transfer function in steady state. For our given system, if we look at G of 0, we plug in 0, we get 20 divided by 2 times 10, which equals 1. So the DC gain of our original transfer function is 1, and we want our reduced transfer function to also have a DC gain of 1. So if we substitute in 0 for s, we need that k over 2 equal 1. Therefore, we need that k equal 2. Therefore, this is our reduced transfer function. And it turns out, if you were to feed a unit step into this transfer function and feed a unit step into this transfer function, you would get very similar outputs. Now we will look at systems that are non-canonical in a different way. So even if we had a second order system, it may not have our canonical form if it has s's in the numerator. Another way to say this is that the transfer function has zeros. So zeros are by definition values of s that make the numerator equal to 0. So they're sort of the counterpart to poles. Poles are values of s that make the denominator equal to 0. Zeros are values of s that make the numerator equal to 0. The effect of these zeros, or how to understand how they change the response of a system, there's a couple different ways to think of it. So one way to think of the effect of zeros is that they affect the contribution of each pole. That is, they affect the coefficients of the partial fraction expansion. So let's say that we have this original system that we used previously. You perform a partial fraction expansion and you solve for the residues, and you get a residue of 2.5 and a residue of minus 2.5. And this sort of demonstrates the contribution of the pole at minus 2 and the contribution of the pole at minus 10. If we change our numerator so that it does have an s in the numerator, then when we do the partial fraction expansion, we'll get different residues. So you can sort of see how the addition of the s in the numerator didn't change what the poles were, but it did change the contribution of the two terms. So just for clarification's sake, let's go ahead and look at these examples and figure out what their zeros are. So looking at the second transfer function, what is the zeros for this system? Since zeros are values of s that make the numerator equal to 0, s equal to minus 20 will give us a numerator equal to 0. So for this second one, there's a 0 at minus 20. For the first term, for the first transfer function, there is no value of s which makes the numerator equal to 0. Therefore, it has no zeros. So this is one interpretation of the effect of zeros. Another way to interpret the effect of zeros is to think of a system this way. So here we have a second order system, but it's not canonical because it has s terms. Specifically, it has a 0 at minus 1. And so we can think of this system, we can split it up into two pieces. This piece has the form of a canonical system. It has a constant in the numerator, no s's. This transfer function does not have the form of a canonical system because it has an s in it. In essence, it's s multiplying a canonical second order system. And so if we think back to what multiplication by s in the Laplace domain means in terms of the time domain, we may recall that multiplication by s is equivalent to differentiation with respect to time. So in essence, we have a canonical second order system and we're adding it to the derivative of a canonical second order system. So looking at this, the way that an underdamped second order system appears, it appears something like this. And so if we're taking its derivative, a derivative graphically is the slope of the tangent at any given point. So if we wanted to graph the time derivative, we can look at the slope of a tangent at every point. So at the beginning, the slope is equal to 0. And then as we go along the curve. The slope starts at 0, and then it gets larger, and then it begins to get smaller again, and at the peak it's exactly equal to 0. So it's 0, and then it increases, and then it comes back to 0. And then after that point, the slope becomes negative. It starts to slope down, and it gets larger negative, and then it gets less negative, and at this local minimum it's back to 0 again. So the value of the derivative is negative, and then it comes back to 0, and then it's positive, and back to 0, and so forth. And as the oscillation dies out, the slopes get smaller and smaller. Another way to think of this derivative, so this is what the step response of an underdamped second order system looks like. If you think about what the derivative of a step is, the derivative of a step is an impulse. So in essence, if this is the step response, then this is the impulse response. So we take this graph and we add it to the second term, which has the form of just a canonical second order system. Between the time at which the step is applied and the peak, we're adding a positive number the whole time. So initially we're adding 0, then we're adding a number that's getting larger, and then at the peak time we're adding 0. And then between the peak and the next valley, we're subtracting a number. And so we dip lower, and then we're back to 0. And then between that valley and the next peak, we're adding a positive number, and so forth. So you can see this red line is with the 0. And you can see how that compares to the standard canonical form. You can sort of see that the oscillation is sort of accentuated. So it reaches its peak sooner, but it has higher overshoot and more oscillation. So for example, this is a graph generated for two transfer functions where the blue line is a standard underdamped second order response, whereas the red line, the red dashed line, is a system with the same poles, the same DC gain, but a 0 added to it. And you can see how it has a higher peak, it reaches its peak sooner, and in essence has more oscillation. So zeros in general tend to have the effect of increasing overshoot and decreasing rise time and peak time. The response is faster, but oscillates more. We will now talk about a couple of exceptions to the trends shown on the previous slide. So in particular, the response shown on the previous slides assumed that the 0 had a negative real part. It was in the left half of the complex S-plane. But if the 0 has a positive real part, then the response will initially move in the reverse direction. And this is called a non-minimum phase 0. And this is an example response. The name non-minimum phase is something that we'll try and explain where it comes from a little bit later in this semester. But the important idea is that when you have one of these, a single 0 with positive real part, in order to make the system go forward, in essence, you first have to go backwards. And there are a couple of examples of this that might be intuitively familiar to you. One, you could imagine sort of balancing a broomstick on your hand. And so if you want to move the broomstick to the right, you kind of need to move your hand back and catch the broomstick and then take it to the right. Similarly, another example is like backing up a trailer. You know, you sort of need to move in the wrong direction initially before you can get it going in the direction that you want. In general, the presence of a non-minimum phase 0 is a bad thing. it makes your system harder to control, as you might imagine. You know, if you have to go backwards to go forwards, that's a complicating sort of issue. Another exception to the rules for the effects of zeros shown on the previous slides is when we have a zero that's near a pole. For example, here we have a transfer function h tilde of s, and it's equal to another transfer function h of s multiplied by the factor s plus z and divided by the factor s plus p. If we have a situation where the z and the p are equal, for example, they both equal 3, then the s plus 3 in the numerator will cancel out the s plus 3 in the denominator, and h tilde will be exactly equal to h. Even if z and p aren't at the exact same location, if they're close to one another, then they approximately cancel. So the effect of that pole and the effect of that zero are sort of canceled out. So for example, let's say that we have this transfer function where we have a 0 at -1 and a pole at -1.1. These two terms approximately cancel, and we can approximate this transfer function as 1 over s plus 10. So they're not exactly equal, but their responses will match up pretty well. So this is another way that we can get a reduced order model. Another example of a type of system that is non-canonical, that doesn't fit our standard form, are nonlinear systems. And so most real-world systems are nonlinear in some respect, and we've discussed a few examples so far in this class. You know, the stiction in a Coulomb friction model, how air drag is proportional to velocity squared, saturation, backlash, nonlinear springs are all examples of nonlinear systems or nonlinear effects. Nonlinear differential equations are difficult, if not impossible, to solve analytically, that is, to solve by hand or to generate a closed form solution for. Furthermore, transfer functions can only be applied to linear systems. Previously in the course, a way that we've shown how to address nonlinear systems or to analyze nonlinear systems is to numerically approximate a solution using simulation. The drawback of this is that it doesn't give a lot of insight. You know, you sort of have this simulation and you can change parameters and run different situations, but you don't see the direct correspondence between a parameter in the system and the output. You kind of just have to, you know, do this sort of guess and check, these experiments, but it's not explicit. You know, you don't have an equation for the output where you can explicitly see what the effect of each parameter is. So this can make it difficult to design your system if nonlinearities are present. An alternative is to try and approximate your nonlinear system by a linear model. A way to get some intuition for this is to think back to something that maybe you did in calculus. That is to approximate a nonlinear function by a linear function. And when we have this situation, so here we have a black line representing our nonlinear function, and we've drawn a tangent at the point x bar, y bar. And so that straight line, if you zoomed in on that point where it's tangent, the straight line will match up very closely to the curved line. If you zoomed way in, you would not be able to distinguish between the two. The straight line would be a good approximation of the nonlinear function. And so in calculus, you may have learned how to find the equation for that line, that linear function that approximates the nonlinear function at that point. And the way that you can do that, one way to do it is to think of the derivative as a finite difference. The derivative at x equals x bar is like the change in f over the change in x. So it's the difference between the y values and the difference between the x values. And then if we rearrange this, we can multiply through by the delta x, we can add the fx bar, and we can get an approximation of f of x. So our nonlinear function is approximated by the y value at that point plus the slope times the delta x. Therefore, we're approximating this nonlinear function y equals f of x as a linear function in terms of delta x, where this is the y-intercept, this is the slope, and this is the independent variable. Something else you may also recognize or remember from calculus is that these are the first two terms of a Taylor series expansion. Another way to sort of rearrange this, so f of x is like our y value, f of x bar is the y value at x bar, which is y bar, and we can rearrange that as delta y equals k times delta x, where delta y is y minus y bar, k is the slope, which is the derivative at that point, and delta x is x minus x bar. So, in a similar way to how we approximated this nonlinear function by this line, we can also approximate nonlinear system models, that is, nonlinear differential equations, by linearized differential equations. So, in particular, we can take a nonlinear differential equation and we can approximate it as a linear differential equation in terms of deltas, in terms of the deviation from the operating point. So this is analogous to what we did with the function, where we took a nonlinear function and we approximated it as a linear function in terms of deltas. We can do the same thing with the nonlinear differential equation. We won't get into a lot of detail about how to derive these linearized models, but we do want to emphasize their usefulness and their limitations. In particular, these approximate models are only valid in a small neighborhood about the operating point. So our operating point, the point about which we're performing our linearization, x bar, y bar, if we look close to that point, the linear function and the nonlinear function match up well. But as we get farther away from that, you can see how they don't match up very well. The same thing is true about the nonlinear differential equation and its linearized approximation. Whatever point we perform the linearization about, the two models will match quite well near that operating point, but as we move away from the operating point, they may not match very well. So here's an example of a car with nonlinear drag, nonlinear air drag. We can derive a model for this where we can derive the differential equation using some of the forces equals mass times acceleration. So the forces acting on the car are sort of the tractive force, in essence the force being generated between the road tire interface and then the air drag. And those equal mass times acceleration, where acceleration is the first derivative of velocity. So this differential equation models this car, and as you can see, it's nonlinear because of the air drag. And so this would be a very difficult differential equation to solve. One option would be to simulate it but the other option is to approximate it by a linear function. Then we can use sort of all of the knowledge that we have learned to perform our analysis and then eventually our design, our controller design. And so the way that we're going to generate a linearized version is to replace each term in that differential equation with its linear approximation. Right? This isn't something that I'm going to have you do, particularly on an exam or in a homework, but I'm just going to quickly go through it once. If you don't understand all of the nuances, that's okay. So recall that we can approximate a nonlinear function, using this approximation, this Taylor series approximation, as the value of the function at the operating point plus the derivative, or the slope, at that operating point multiplying delta v. So in this case, the operating point needs to be an equilibrium, or the point that you're performing the linearization about is an equilibrium point v bar f bar. So it's a velocity and a force that put the system in equilibrium. That is, so it's not accelerating in essence. At this equilibrium point, the air drag is exactly balancing the tractive force, and the car is not accelerating. So we're going to replace this nonlinear term using something like this Taylor series expansion. And then we're also going to replace the forces by this term and the velocity by this term, where delta f is the difference between f and the operating point, and delta v is the difference between v and the operating point. So the deltas are in essence how far away is the system from the equilibrium point that we're performing the linearization about. So this has the form above here. So this is f of v bar. This is the function at v bar. This is the derivative evaluated at v bar. So df, dv, you bring the 2 down and you subtract 1 off the exponent. So the derivative of this is 2 times b times v, evaluated at v bar, and then multiplied by delta v. So we replace this term by this term, and we replace the f and the mv dot by these terms. So we replace the f by f bar plus delta f, and we subtract this linearized version. And then we substitute in for v dot. If we're going to take the time derivative of this, v bar is just a constant, so its derivative is 0. And then we have the derivative of delta v. So, and then looking at this, since in equilibrium the tractive force exactly offsets the air drag, this f bar is going to be exactly equal to this b v bar squared. So since we have a negative sign there, those two will subtract. Plug those in, and our linear approximation is delta f minus 2b v bar delta v equal to m times delta v dot. And so this is what we were saying previously, that we are going to approximate the nonlinear differential equation by a linear differential equation in terms of the deltas. So, we have no squareds, we have no sines, any nonlinear functions of delta v or delta f. The thing to recall here is that this approximation works well as long as delta v and delta f are small. As long as the conditions are such that the system stays near the equilibrium point v bar f bar. Since we have a linear differential equation, we can then do all of the analysis, all of the things that we've learned so far in the course. In particular, we can find the Laplace transfer function for this system. Take the Laplace transform, assuming zero initial conditions, rearrange it into the form output over input. We can get a function delta v of s over delta f of s, where the attractive force is the input and the velocity of the vehicle is the output. If we wanted to actually use this linearized model for analysis, we would need to be able to transform the system back from being in terms of the deltas to being in terms of the absolute velocities and absolute forces, because that's ultimately what we care about. So for example, in this, if we were to build a Simulink model, we could imagine it looking like this. So this is our plant linearized model that we just found. Delta v over delta f, where delta f is our input and delta v is our output. But our true input isn't delta f, it's f. And we just recall that delta f is f minus f bar. It's how far away is the force from the equilibrium point, the operating point that we linearized about. So here's f, here's the nominal force, f bar. We subtract them, and that gives us our delta f. And then we get an output delta v, but again, what we really are concerned with is the overall velocity of the vehicle. And so in order to get v back, we need to add the delta v to the operating point v bar. And that gives us v, or at least a linearized approximation of the velocity. So that brings us to the end of Module 12. So in this module, what we've addressed are systems that don't fit the form of a standard first order or standard second order system. And what we were attempting to do is two things. One is to understand systems that don't have a canonical form. For example, higher order systems and systems with zeros. And so the way that we address this is higher order systems we are able to think of as the sum of first order systems and second order underdamped systems. Another way in which a system is non-canonical is if it has s terms in the numerator. That is, it has zeros. And we saw that the effect of a zero tends to cause the system to be faster but to overshoot more. Two exceptions to that case were one, non-minimum phase zeros, i.e. zeros that have a positive real part, and zeros that are canceled by poles. Aside from trying to predict or understand non-canonical systems, we also wanted to understand how to create simpler models, to take these non-canonical systems and approximate them by canonical systems, canonical first order, canonical second order systems. One way that we can do that is if there are very fast dynamics in the system. The rule of thumb that we'll go ahead and use is if the real part of any of the poles are more than 5 times faster than the other poles, then we can approximately neglect its contribution to the dynamics, though we can't neglect its contribution to the steady state behavior. We also saw that when a pole was near a zero, they approximately cancel, giving us a possibly reduced order model. And then finally, when we have nonlinear systems, we talked about very briefly how to generate a linearized approximation of that nonlinear system and how useful that linearized model is. In particular, how it's only really useful in a neighborhood about the point at which the linearization was performed.